Well, good morning, everybody. It's a pleasure to have you here. Antonio is an engineer. He worked here with Professor Enio in the hydrogen laboratory. And now he's in Hytron. Hytron is a spin-off of Unicamp. And the expertise is about gases, hydrogen production, but not only that, renewable energy also. And they worked on the implementation of many photovoltaic systems in São Paulo, in other states, isn't it? And we will talk a little bit about hydrogen production concerning the use in vehicles. So it's the mobility use of this substance. Okay? Thank you, Antonio, for your presentation.
I would like to thank Professor Carla, Professor Flavio for the invitation. It's a pleasure to me to be back home to share a little bit about our expertise in hydrogen production and its utilization in the new growing energy market. Our agenda today is to cover a little bit about the company history and activities, the actual hydrogen market, its applications and hydrogen solutions for that, the emerging energy application, as I told you, examples and some specifications of fuel cell hybrid electric vehicles, a special case of ethanol as a source of hydrogen for electric vehicles, examples of worldwide projects concerning hydrogen and its utilizations, the new applications of hydrogen as a raw material for renewable hydrocarbons production, including a Brazilian jet fuel scenario, distinct technologies for sustainable aviation fuels production, and specifically in the route of Fischer-Tropsch synthesis, since it's a route very related to hydrogen and hydrogen technologies, and additional opportunities for Brazil. So Hytron is a technology company founded in 2003, right here in Unicamp. Hytron is a spin-off of the hydrogen laboratory in Unicamp. You know Unicamp very well. I don't need to talk about it. We were pioneer in producing hydrogen from ethanol, and our team is specialized in innovative projects, technological projects concerning hydrogen and other industrial and special gases production, special since as carbon monoxide, for example. And also, as Professor Carla told us, in alternative energy generation. So our activities are focused in two main areas, energy and gases, including on-site generation of gases, power to X, which is a new terminology for energy applications of hydrogen produced from alternative renewable sources, energy storage using hydrogen or using lithium batteries or flow batteries, PV power plants, and Internet of Things. And we keep, of course, since we are a technological company, we keep continuous research and development inside our company, sustaining our products and develop new products and new opportunities for the company and for the country. This includes alternative sources for hydrogen production, trying to bring the cost down of the produced hydrogen, waste heat recovery from processes, and energy storage alternative technologies. To understand why Hytron does what it does, it's very important to understand the hydrogen market and the conditions of Brazil. In Brazil, the main hydrogen sources are the refineries. Refineries are big plants of hydrogen, but the refineries are located in the coast of the country. In the same moment that the industry is developing in the countryside, inside the country. So the hydrogen consumers are very far away from the hydrogen sources, and it's very important to know that if you away more than 500 kilometers from the hydrogen source, the cost of freight it's more expressive than the cost of hydrogen itself. So in this scenario, Hytron developed on-site solutions for hydrogen production. Solutions that are located together with the consumers, near to the consumers. In order to do that, we are very dedicated to optimize the operational costs of our technology, since for small hydrogen plants, operational costs are more expressive in the final hydrogen cost than the investment cost itself. So in order to keep our OpEx low, we need to be efficient. And when we are efficient, we are able to attend other markets, other emerging markets, as I told you, such as the energy market. So this is the background of on-site solutions developed by Hytron. When we talk about on-site solutions, we are talking about sustainability because there are no carbon emissions related to the transportation of the product, hydrogen itself. We are talking about reliability because in Brazil only trucks are used to transport hydrogen. And our highways are not always very good transportation routes. So sometimes the consumers are not well attended because the company was not able to deliver hydrogen at time. So when you produce hydrogen locally, you are able to operate more in a more secure way. So today, hydrogen is used for production of chemicals and pharmaceuticals, chemicals specialties, for the semiconductor industry, for the hydrogenation of oils, especially in Brazil. And for example, Cargill, it's a worldwide recognized company, and Cargill is recognized for its capability to process soybean oil. And some plants in Brazil, Cargill have more than 800 products derived from soybean oil that uses hydrogen as raw material. So in only one plant of Cargill, you have at least 100 products derived from soybean oil that uses hydrogen as a raw material. These products are used for hygiene, are used for specialties in the food industry and many other applications. Flat glass production demands hydrogen as a raw material as well. The power industry, metallurgy, and as we keep talking, the new energy applications of hydrogen as an energy vector. In order to attend this market in Brazil, in Latin America, and even in other countries of the world, Hytron developed two basic lines of products. The first one, fuel reformers. We focus on natural gas. Natural gas today delivers a less costly product, a less costly hydrogen than ethanol, but ethanol is very strategic for Brazil, and because of that, because of the tradition of the ethanol industry in Brazil, we developed an ethanol reformer in order to generate from a hydrocarbon a renewable hydrogen as well. Our systems are integrated and autonomous. Our supervisory platform are developed inside our own company. Concerning reformers, our product capacities is up to 30 kilograms of hydrogen per hour, stand for something like 300 cubic meters per hour, a little bit more than this. Purity is up to 6 nines, which represents 99 point and other 4 nines after comma of purity, and typical operating pressures of 10 bar. It's a very important issue because this pressure attains 8% of the consumers' required pressure. And this pressure dispense, for example, additional compressors, additional costs, additional investment. So, in most cases, reformers are assembled inside a container, tested in our facility, and very efficiently delivery in field, reducing time to put the system into operation in our customers. These are very interesting indicators related to the natural gas use for hydrogen generation. So we have a specific consumption of about a little bit less than 5 cubic meters of natural gas for each kilogram of hydrogen produced. The same indicator for water, which is other necessary raw material, a little bit less than 21 liters of water per kilogram of hydrogen, and electricity in the order of 4.7 kilowatt hour for each kilogram of hydrogen produced. This is a very interesting indicator as well, because when we compare this indicator with water electrolysis, this is the amount of energy required to generate only 1 cubic meter of hydrogen. And when we talk about reformation of hydrocarbons, this is the amount of energy required for 1 kilogram. So this process is about between 11 and 12 times less electricity intensive than water electrolysis. So this is a very important trade-off in some scenarios of hydrogen production. The reformers use the process of steam reformation of the hydrocarbon, combined with post-processing of the reformate and the hydrogen purification through PSA, which stands for pressure swing adsorption systems, purification systems, in order to achieve purities such as this value mentioned. In the case of ethanol reformers, those are the indicators. We require even less electricity in the case of ethanol. This is very interesting as well, because for natural gas, in order to produce pressurized hydrogen, we need to pressurize natural gas. So every time you compress gas, you have to spend more energy, more electricity in order to do that. In the case of liquid fuels such as ethanol, it's less electricity intensive than gaseous raw material, and this is a very important advantage of ethanol over natural gas reformation. This is a simplified block flow diagram for the reformers. So in our process, we have a reformer furnace, which is also responsible for the heat generation for the whole system. In this furnace, we reformate the hydrocarbon together with steam in order to produce a mixture of gases very rich in hydrogen, carbon monoxide, and a little and other gases such as residual methane, ethane, and a little bit of nitrogen because natural gas has a little bit of nitrogen. And this stream is post-processed in shift reactors that converts the carbon monoxide together with the steam in additional hydrogen and carbon dioxide. So in the output port of our reformers, we have a very concentrated hydrogen stream, which is delivered to a PSA system in order to purify. A PSA is a separation process that receives reformate with up to, let's say, up to 74% of hydrogen, delivers purified hydrogen in one port and a fuel stream in the other port. This fuel stream contains hydrogen, contains all the other contaminants, and this stream is used to generate heat in our reformer furnace. In this integration, with this integration, we are able to operate in a very efficient way because we don't need ethanol or natural gas to generate heat in our furnace. We use our raffinate, we use our process byproduct to generate heat for the process. This is a way to operate efficiently and bring the costs down of the final product, which is hydrogen. In the case of electrolyzers, we work with both PEM or alkaline technologies. In case of alkaline technologies, we have our own technology for stacks, for water dissociation modules. So in the case of alkaline technology, we are responsible for stack and for the whole Belisol plant around stack, including hydrogen purification, purity monitoring, etc. In case of PEM technology, we are responsible for the whole system, but the stack. We have a US partner that provides us with the PEM stack, and we are responsible for all the other tasks necessary to do an integrated plant based on PEM technology. In case of water electrolysis, we are able to produce up to 40 kilograms per hour of hydrogen with the same level of purity and pressures up to 40 bar, considerably higher than the reformers, and very important, and we will see this a little bit away, how this pressure is important for applications concerning synthetic fuel production. So this is a picture of a PEM electrolyzer manufactured by Hytron, and the system installed in the field. PEM, it's a very interesting technology, very interesting when compared to alkaline, because PEM technology have a high power density. This is the PEM stack right here in the center. This is it's like a half the size of this cabinet, and it's capable to absorb 1,000 amperes, able to produce up to 22 cubic meters of hydrogen per hour. So it's it's a very powerful technology. Also, PEM have a very high turn-down ratio. This means that this technology is able to produce hydrogen from 5% of nominal capacity up to 100% of nominal capacity. This is an indicator which alkaline technology can accomplish. Alkaline technology operates typically between 30% and 100%. It's capable to, since the technology operates with a high current density, the technology is also able to respond to fast variation of charge. And this is also a very important issue when we consider the integration of the electrolyzer with seasonal power sources such as solar, such as wind, and etc. And we don't need further purification for the hydrogen stream coming out of the stack, because the electrolyte is a polymer-based material, so it seals the hydrogen circuit from the oxygen circuit. So directly from the stack, we are able to produce hydrogen up to 5 nines of purity. Other interesting aspect is the differential operation, differential pressure operation condition. That means that I can produce hydrogen at 40 bar in one circuit and oxygen at atmospheric pressure in other circuit, because of the design of the engineering of the stack. From the energy point of view, this is very interesting because I don't have to expand the amount of energy required for the oxygen electrochemical compression, since I won't use the oxygen as a valuable product. So I'm able to save a little bit of energy operating in this condition. Of course, to deliver high purity hydrogen, we have to have additional competencies, such as the capacity of design and manufacture purification systems for hydrogen and for other gases. Here we are talking about PSA system, pressure swing adsorption systems. And of course, the catalytic, the thermochemical processing of the working Asian stream. Right here we use catalyst process such as desulfurization shift or reverse shift sometimes, methanation, partial oxidation, and deoxidation of the gauge streams, depending on the process, depending on the product we are aiming for. So, until now, we were able to discuss technology that is ready to attend to industrial applications of hydrogen. Right now, we are able to discuss the newer applications of this vector. And these newer applications are defined as power to X. Power to X stands for the use of electricity, sometimes the surplus electricity, to produce hydrogen and use this hydrogen in alternative applications, such as energy storage, converting power into hydrogen, and when necessary, hydrogen into power again. In order to produce hydrogen to fuel hydrogen fuel cell hybrid electric vehicles, or when a source of carbon is available, use hydrogen and the carbon dioxide to produce synthetic gases such as synthetic natural gas or electrochemicals. The E stands for electrochemicals, since I have a hydrocarbon that was generated from electricity, basically. So this is a new terminology of hydrocarbons generated inside the concept of power to X. So in the first application of hydrogen from produced in the power to X context, we are talking about the direct use of hydrogen inside a fuel cell electric vehicle. So no matter what the manufacturer of the vehicle, this is the typical components inside a fuel cell electric vehicle. We have the hydrogen tanks, almost always positioned in the back of the car. Right now, the manufacturers are working with 700 bar as a storage pressure for hydrogen in order to achieve more than 600 kilometers of autonomy for those vehicles. Today, all hydrogen cars are hybrid cars. So inside the cars we have a battery, a lithium battery pack, in order to, the concept is the same used for internal combustion engines hybrid cars. If you have a small pack of batteries, you are able to optimize the operation of your power generator. So you are able to consume less hydrogen for each mile or each kilometer per kilometer. The fuel cell generates electricity in DC mode. Sometimes the manufacturer uses DC motors as a traction motor. In this case, you need a DC-DC converter in order to control how much power you want in your wheel. And some power, sometimes manufacturers use AC motors, traction motors, to move the car. And in this case, instead of a booster, they use an inverter to control speed in the car. This is I bring you some information about Nexo, Hyundai Nexo, not for particular reasons other than are very much available information about this car, more than for other suppliers. So Nexo is a medium SUV for US standards. And it's very interesting in Europe. Hyundai promote this advertising. They put Mireia Belmonte, which is an Olympic swimmer, running inside a dome, connected to the tailpipe of the car, to demonstrate that the air used to feed the fuel cell cistern and the tailpipe is cleaner than the air in the atmosphere. So we keep she running for a time, of course, matured, but it was a very aggressive advertising, very important for the technology. From a technical point of view, Nexo was approved for as a top safety plus. Is the same price, for example, that Tesla Model S wins concerning safety when in crash tests in America. And this is new for hydrogen vehicles, because there is no further information concerning the behavior of the fuel storage in the crash test conditions. So was very important for the technology, this demonstration. Nexo was an evolution from Tucson fuel cell SUV. And in this technology, Hyundai was able to increase power by 20%, increase efficiency in 5%. The powertrain, the fuel cell generator inside the Nexo SUV have approximately 60% of fuel efficiency. This is very, very, very important, because the best engines for cars today have efficiency of about 35, perhaps 40% in some conditions. F1 engines are able to provide something close to 50% today. But for regular technology, for day-to-day technology, engines are between 30 and 40%. So 60% is considerably higher than that. And this is very important from the OpEx point of view. And if we think about it, we see this today for electric cars. The problem, not the problem, but the situation for electric cars, pure electric cars, only with batteries, they require a high investment, a high capex, but it's very cheap to operate because in electricity is cheaper than hydrocarbons to fuel a car today. And with this efficiency of conversion of hydrogen into electricity, this corroborates, of course, to make the operational costs of this car as cheap as a pure electric vehicle. It's very interesting to note as well the driving range for Nexo SUV is 308 miles. It's close to 610 kilometers. So it's very comparable for today's gasoline or even a small ethanol internal combustion engine car. But there are many other interesting data and information. The presentation will be available for everyone. A very interesting case is the consideration of the use of ethanol as a source of hydrogen for fuel cell hybrid electric vehicles. As I told you earlier, our fuel reformer, our ethanol reformer requires 7.6 liters of ethanol in order to produce 1 kilogram of hydrogen. So if we took this number and put this together with the fact that this car, the hydrogen cars usually have 5 to 7.5 kilograms of hydrogen inside a car, stored as a compressed gas. Still, together with the information of Bosch, for example, Bosch is a partner very close to us. They recently acquired a Swedish company called PowerCell, which is specialized in develop and produce fuel cell systems. So if we consider a small car, which up to 1.5 tons of weight, the specific consumption of this car is about 150 kilometers per kilogram of hydrogen. So considering this specific consumption and the amount of hydrogen inside the car and the amount of ethanol necessary to produce 1 kilogram of hydrogen, if we do the math, we for fuel cell hybrid electric car fueled with hydrogen from ethanol, we have a specific consumption of close to 20 kilometers for each liter of ethanol spent. It's a very interesting indicator because this number today is above the specific consumption of, for example, the hybrid Corolla, which was the first flex fuel hybrid vehicle in the world. Today, I think the Metro officializing numbers close to 14 liters of ethanol per kilometers. Okay, in real life, perhaps it's a little bit higher than that because the procedures of the Metro it's not optimistic for real life. But even considering 16 or 17 kilometers for each liter of ethanol, we are expressively higher in this scenario. Brazil had a fuel cell bus project. The project was responsible to produce 4 buses that operates in São Paulo by EMTU, which is Empresa Metropolitana de Transporte Urbano. The suppliers for the fuel cell system and for the hydrogen refueling station was Canadian companies called Ballard for the fuel cell technology inside the vehicle, and Hydrogenics for the hydrogen refueling station. So the quality of the hydrogen produced was defined by a standard which already exists, defined by SAI. SAI J2719 defines the specification of hydrogen as a fuel for fuel cell hybrid electric vehicles. The buses had 45 kilograms of hydrogen at 350 bar, and the Brazilian project was able to deliver a specific consumption of 15 kilograms of hydrogen for 100 kilometers run with the bus. For comparison, and Cute, which was a European program, was able to demonstrate a specific consumption considerably higher than the Brazilian project. So was a very important goal of Brazilian project. The autonomy range of the buses was 300 kilometers, and the buses was composed by 2 fuel cell stacks delivering up to 120 kilowatts power. In that time, the system was hybridized with Zebra batteries, responsible to deliver up to 108 kilowatts, and had 2 electric traction motors with a power up to 300 kilometers. The project was finalized. Today, the buses are not running anymore. But all the information are available in a publication from the project called Ônibus Brasileiro a Hidrogênio, Tecnologias Renováveis para o Transporte Urbano no Brasil. This is a pressed report. I think it's available on the internet. Some pictures of the bus, another bus, and some pictures of the fuel station. It was installed in São Bernardo do Campo, metropolitan region of São Paulo. Of course, it's not happening only in Brazil, it's happening all over the world. The most recent news are talking about the use of hydrogen as a fuel for trains, especially in Europe. This is a particularly interesting case because all trains, at least the most of them in Europe, are already electrified. But this mode of transportation are electrified by a grid, a network to deliver electricity to the vehicle. Even considering expensive technology, when you compare only the car, the electric car and the hydrogen electric car, in the case of hydrogen, you don't need a grid to deliver electricity to the car. And this is a very important trade-off that is making the hydrogen technology feasible in today's scenario for Europe. So it's a very expanding application of hydrogen, not only in Europe, but also in China. Toyota is very involved with trucks because trucks, differently from the small light cars, it's very difficult to electrify a truck because for let's say 1,000 kilometers required for a truck, the amount of batteries is so big that you lose payload. You lose payload. You lose capacity of load transportation. So in this particular case, hydrogen has this important trade-off over electrified trucks, electrified only with batteries, and this is also a very important niche developing in Europe, developing in the US. It's more important application for the US. Of course, Toyota is also involved with small cars. This is the Mirai. I think this is the third generation of Mirai small passenger car. The Europe, specifically DLR in German, the DLR is the space, the aeronautical and space agency, but for Germany. They are working with small airplanes fueled with hydrogen and propelled by fuel cell system as well. So this is a four-seat small airplane for 4 passengers called Antares. Very, very interesting project. I had the opportunity to know the airplane. Very, very, very nice project. As I told you, trucks are very important for US specifically. This was not anymore, but Nikola was a startup in the US. Today they are focusing developing 3 products, 3 different trucks fueled by hydrogen, powered by fuel cell systems. And Nikola today owns it's a $3 billion company, receives the financing from several big companies all over the world, including Bosch, because Bosch, that acquires PowerCell from Sweden, is now an investor in Nikola because Nikola uses PowerCell fuel cell in order to power the vehicles. So there's a lot of press news telling us what is new with those companies. It's very easy to find this news in the internet today. As I told you, for China expects to count with hydrogen for 10% of its energy network by 2050. So considering the energy matrix of China, 10% is a very, very big number. So it's a very expressive information. This is a software developed by Now, which is a German agency. And this app show you all the hydrogen refueling stations in operation, where they are, the price of the hydrogen, the stations in homologation, the stations under construction. It's a very interesting app. It's possible to download in App Store, Apple Store, or Android, whatever. And it's very important to keep eyes on this type of information. This is information from Nikola as well. When we talk about trucks needs fueling station because they actually have to go from one side to another of the country. So they expect to have 700 stations by 2028 in order to attend 14,000 trucks in the same day. This is the expectations of Nikola by 2028. Only Nikola had supplied up to 14,000 fuel cell electric trucks. Well, until now we discussed the direct use of hydrogen in mobility, but as I told you, hydrogen is also a raw material for, let's say, hydrocarbon production, and these hydrocarbon, when used in conventional vehicles, internal combustion engine vehicles, in a way, they are fueled by hydrogen. They are fueled by hydrogen produced by electrolysis, by reforming of ethanol. They are also fueled by hydrogen in a way. So if you have water, if you have a source of carbon dioxide, for example, if you took carbon dioxide directly from air, or if you capture ethanol from ethanol or biogas plants, or even if you recover carbon dioxide, I said ethanol, but no, if you took carbon dioxide from air, or carbon dioxide from ethanol or biogas plants, or even if you recover carbon dioxide from consolidated industrial process, you are, when these processes are sustainable, when these processes are renewable, you have a cyclic source of carbon dioxide. So you don't put additional carbon dioxide into atmosphere. You only recycle the already existing carbon dioxide. If you combine this carbon dioxide, which is a source of carbon, with hydrogen, for example, from water electrolysis, using electricity from renewable sources, you have renewable chemicals. If you have a process to synthesize hydrocarbons from this stream, the hydrogen and carbon monoxide stream, which is called synthesis gas, because it's a stream used for synthesis processes, you are able to have synthetic hydrocarbons. And in this presentation, I will focus a little bit more into kerosene, especially into jet fuel, aviation kerosene, because this is a product with high market value, and today Brazil doesn't have the capacity to produce our own consumption of jet fuel. So since the fuel is used for the aviation sector, the aviation requires high autonomy for big airplanes. The same condition we discussed for trucks, we have in the airplanes. Actually, it's a more difficult condition, because in order to give for a large airplane an expressive range, expressive autonomy, you have to put so much battery inside it that you are not able to transport people, actually. So since the batteries technology are not ready right now to attend this sector, if you are able to switch the fuel from a fossil source to a renewable source, it is already a gain for the planet and for the sector. Together with this, as I told you for batteries, the aircraft aviation demands very high mass and volume densities, because it's a very important issue for powertrains in aviation. Standardization is essential. When we talk about specifications for jet fuels, this is a big issue. It's extremely expensive to certify a new fuel for aviation. ISTM has a prediction that costs close to $10 million, and you need 10 years to certify a brand new fuel for an aviation application. So this is the cost financial and time cost in order to certify a new fuel for the aviation sector. For this reason, aviation will remain to rely on like liquid fuels. It's not ready. We don't have technology to electrify aviation right now. Because of this, it's important to develop process in order to produce improved fuels to attend this market. Together with this, we have an estimative that more than 99% of aviation emissions and approximately 50% of airport emissions are related to combustion of jet fuel. So sometimes this 99% of aviation have a special problem because these emissions are emitted in the higher atmosphere. So sometimes this is even worse in the climate context. There is another estimative that aviation accounts for approximately 2.5% of anthropogenic global carbon emissions. And because of this, programs such as CORSIA were created. CORSIA was created in 2016. And CORSIA defines a cost for the carbon emissions specifically for aviation. And the cost is higher and higher in the next coming years. And this is a way to try to improve the supply chain and the process involved in the supply chain of the aviation sector. This is what the sector requires worldwide, but in Brazil, especially in Brazil, not all the refineries are prepared to produce kerosene, jet fuel kerosene in Brazil. Only some of them, and 80% of the production of jet A1 kerosene in Brazil are located in the southeast of the country. Of course, we have a distribution logistic all over the country, but the consumers are pretty much spread all over the country. Sometimes very far away from the production or from the distribution points. Some cases in the north of the country, each liter of jet fuel requires 8 liters of jet fuel to be delivered. So the relative cost of this jet fuel and the relative emissions of this jet fuel used in the north of the country is very, very high and very distinct of our situation in the southeast of the country. It's a very interesting scenario in Brazil. Together with this, we have a forecast. Our production is stagnated around 6.5 billion liters per year. The demand are growing, importation are growing together with demand. And there is a expectation in 2050, we have to import more than we produce producing today in Brazil. In 2050, according to EPE, we probably will need to import something about 8.2 billion of liters of jet A1 per year. In order to attend this market issue, are under development several routes for sustainable aviation fuel production. Of course, we can co-process vegetable oils together with oil crude in the existing refineries. There is alcohol to jet, a route called alcohol to jet. You remove the hydroxyl from ethanol, produce a 2-carbon chain, And through oligomerization, we are able to produce, for example, a 8-carbon chain, which is equivalent to jet fuel, from ethanol, let's say. This is one route. In this case, the already existing standards permit that I drop in 30% tops of this jet fuel in a fossil jet fuel in a fossil jet fuel stream. Other than that are other routes such as synthesized isoparaffins. HEFA is it's a very important route as well. Uses vegetable oil, hydrogenate this hydrotreat these vegetable oil streams in order to produce an equivalent to jet fuel. And of course, there is a Fischer-Tropsch route that uses synthesis gas, as I told you, a stream composed by hydrogen and carbon monoxide to produce any desired hydrocarbon, including aviation kerosene. For HEFA and for Fischer-Tropsch, ASTM allow me to drop in up to 50% of this new renewable sustainable fuel. For obvious reasons, since Fischer-Tropsch is a hydrogen-dependent route, we are focused on Fischer-Tropsch. Fischer-Tropsch is a synthesis process that uses synthesis gas in order to produce a family of hydrocarbons. It's a complex chemical system. Of course, we are able to optimize the species we are looking for, but we always have associated hydrocarbons together with the desired hydrocarbon. So this is the typical hydrocarbon distribution coming out a Fischer-Tropsch reactor. So I had to use this stream called crude, as we call crude for the oil, for the crude from petroleum, for example. But this E-crude, we use this E-crude to produce any desirable hydrocarbon. And in this route, we are able to substitute typical petrochemical routes for new hydrogen-based routes in order to produce the same products that are necessary for today's society. In this context, the German government, through GIZ, which is a technological cooperation agency, is developing with the Brazilian government one project called ProKeeper, which stands for Pro Querosene Renovável. In this project, we are trying to demonstrate carbon dioxide and water captured directly from air, together with the use of renewable electricity in order to electrolyze both water and carbon dioxide and generate hydrogen from water and carbon monoxide from carbon dioxide. Since I have hydrogen and carbon monoxide, I have a synthesis gas stream, and feed a Fischer-Tropsch reactor with this stream. With the stream produced by water and carbon dioxide generated from air. So if I feed a Fischer-Tropsch system, if I feed a Fischer-Tropsch plus an upgrading system with this synthesis gas, I'm demonstrated that I'm able to produce jet fuel from renewable electricity and air. So it's a very, very beautiful project because demonstrates the technical feasibility of produce hydrocarbons from electricity and air. Of course, air as a source of carbon dioxide and water. So ProKey is on-site, renewable, autonomous, and decentralized micro-refinery solutions. Because what ProKey aims is to attend those consumers very, very away from the production points in Brazil. For those applications located in the north of the country, it's this jet fuel doesn't have to compete with the price of the jet fuel right here. This jet fuel had to compete with the price of jet fuel in that location, which is 9 or 10 times higher than the price of jet fuel right here. So this is the main objective of this project. Of course, it took in this, let's say, this not well attended consumers as a niche to develop technology, to bring the cost of the technology down, and of course attending more and more consumers, even closer to the production of the production sites for cures. The group, the team, the technical team, of course, are looking a step ahead of ProKey itself, and we are still working on alternative sources of synthesis gas, because of course it's very interesting to produce synthesis gas from air to electrolysis, but this synthesis gas it's of course more expensive than a synthesis gas, for example, produced by a byproduct from biodiesel industry or from biogas existing on biogas plants. So the technical team are looking ahead into the use of glycerin, for example, as a source, as a hydrocarbon, able to produce synthesis gas, and able to feed the Fischer-Tropsch unit, and produces a high valuable products such as Jet A1 or aviation gas, gasoline aviation, or diesel, or LPG, or special chemicals for hygiene or whatever from a byproduct. So if I dealing with a byproduct, I dealing with a low cost raw material, and if I'm able to produce synthesis gas from this low cost raw material, I'm able to produce a low cost final product. This is the strategy. In the same way, and I always bring a picture of Brazilian map, because the picture is able to show us that the biodiesel plants, for instance, are closer to the not well attended consumers than the refineries. They have all the refineries are over here, biodiesel up to here, and I have consumers more closer to biodiesel plants than to the refineries. So if I produce, let's say, Jet A1 in these plants by using an alternative route, I bring the cost down to attend, for example, consumers in locations near of this state. The same happens with ethanol industry. In this case, ethanol, it's able to provide very well, very high concentrated carbon dioxide streams, because when I have to separate, when I have to capture the carbon dioxide from air, I have to capture 300 ppm of carbon dioxide present in the air. Of course, there is a energy cost related to that, and if I have the opportunity to use a carbon dioxide stream from ethanol industry, which is a concentrated stream, it's cheaper energy and financially to use this carbon dioxide stream and capture from air. And of course, ethanol spread all over our country. It's a very important source of carbon dioxide for other hydrocarbons production other than ethanol hydrocarbons production. And in the same sense, I have several biogas plants in Brazil. Biogas can provide me with methane and carbon dioxide, both sources of carbon, and both usable in order to produce synthetic hydrocarbons from these sources. So in a general way, this is my message today. I appreciate one more time the invitation. It's really a pleasure for me to be here, and I'm available for any further questions.
Okay, thank you, Antonio.
My pleasure.
So you guys, now it's time for questions. People who is working with hydrogen production, as I can remember, fuel cell vehicles as the project proposal, as I can remember. So you can ask whatever you want to Antonio. He can help us in this.
I can try to.
I have 2 points. One, you told you don't usually use the oxygen produced in the plants, in the electrolysis. Is because it's not worth the cost to use, or?
Yes, it's because the oxygen, the electrolytic oxygen, it's more costly than the consolidated sources that we use today. Today, oxygen is produced as an air product, so it's produced by air distillation, and it's a very, very consolidated process, and the costs are very, very. It's a very cheaper process than compared to the electrolysis in order to generate.
But
oxygen.
since you already use the electricity to generate the syngas,
Of course,
you could use like higher purity maybe this gas than the other get by distillation, or no?
No, the distillation is able to produce
Even better.
very pure oxygen as well. Depends on always depends on the site where you are located. If you have an oxygen demand near your electrolyzer, and if you are producing hydrogen and have this byproduct, the oxygen byproduct, if you have the demand, of course, okay.
Like
perhaps
you could adapt the unit to also get
Yeah.
the
Could be
oxygen.
feasible, economically feasible to use that oxygen, but it's not feasible to implement an electrolyzer to produce oxygen.
Okay, yeah.
Only to produce oxygen.
Yeah, I thought only to take advantage is already there, so take the oxygen and sell
exactly.
to
You have to take advantage
the hospital nearby.
of the-
And the other question is, which catalyst you use in the CO2 reduction before, in the last concept you showed?
The CO2 reduction, you mean the use of CO2 to generate carbon monoxide?
Yes.
That depends. We use two routes. The first one, as I told you on ProCare, I have an electrolyzer for carbon dioxide. So it's an electrochemical process in order to convert carbon dioxide into carbon monoxide.
Yes.
In this case, my catalysts are nickel-based.
Nickel-based.
Nickel-based, so it's cheap catalysts. A alternative route, if I don't want to spend electricity to produce carbon monoxide from carbon dioxide, I am able to implement what we call a reverse shift reactor. So shift reactor typically converts carbon monoxide and steam, water steam, into hydrogen and carbon dioxide. A reverse goes on the other way. I use carbon dioxide and hydrogen in order to produce carbon monoxide and steam. In this case, I use platinum-based catalysts in order to do that. It's platinum, it's a noble metal, but it's very high dispersed catalyst. So I use less than 1 milligram.
Per unit.
Yeah, per, let's say per gram, in order to, per gram of catalyst, in order to do this process.
In the electrolysis, like the work electrode is nickel based and the counter as well, or
No, it's
graphite?
electrolyzers. You don't have a counter electrode. You have a
But like-
bipolar electrode.
Both electrodes are the same.
Yeah, not exactly the same, but it's a small variation. A small variation. In the cathode, you usually generate hydrogen or carbon monoxide, and in the anode, you always generate oxygen for this chemistry.
Thank you.
More questions, you guys? No?
I had a question. Your company also works with pyrolysis processes?
We cooperate in a pyrolysis project. In this case, we work with rotary kiln, slow pyrolysis.
Okay.
Because fast pyrolysis is a very consolidated process to generate bio-oils from biomass. The slow pyrolysis, it's a process that produces gases, more gases than bio-oils from biomass.
Okay.
So since Hytron is more interested in the gaseous routes, we work with this technology. As well, we work with gasification, for example.
You said that your lower limit was like 60% hydrogen before you were willing to separate it out, or like
60.
I used to work for a company that had a pyrolysis process,
Okay.
and they had difficulty because the process had a large quantity of different gases. You had hydrogen, CO2, CO, but the most they were able to get to is about 60% hydrogen. What's like the lower limit that a PSA, like a purity that you could start trying to separate out the
We are
gases?
talking about the hydrogen upgrading.
Yes.
Okay,
Like splitting these process streams off.
Actually, there is no technical limiting. You have to make the calculations to determine the economical feasibility. Because PSA is able to upgrade a very poor grade hydrogen. But when you have smaller amounts of hydrogen in your inlet stream, you don't have a very good recovery index, which is a very important parameter in PSA systems.
Okay.
So your efficiency is low. If you have to make an investment in a non-efficient equipment, you are perhaps not all you can pay your investment.
So
off.
it's not a physical problem. It's more just an efficiency.
Yeah.
Okay.
Yeah, it's about that.
Your company also works in like say, a lot of these processes have tars, waters, and
Yes.
other impurities. Your company also works with that aspect of gas purification?
Yes, we have to.
Yeah.
Especially in pyrolysis. The tar formation in process, both for pyrolysis or gasification, the tar formation is very related to several parameters in the process. For instance, granulometry of the biomass. If you have a very small biomass being processed, you have less tar in your product stream. If you are able to provide the process with some steam, the steam helps to bring the tar down, the tar concentration down. Doesn't matter. how much you try to avoid tar, you always have tar because it's a predictable, it's a thermodynamic predictable product in your complex chemical system. So you always have tar in your product stream. So for that we work sometimes, depending on the amount of tar, with oxidation, preferential oxidation of tar. So let's say you took your product stream, add some air, small amount of air because you are not able to make this explosive, a small amount of air, and put this stream with air inside a catalytic reactor in order to oxidize tar into smaller hydrocarbons.
Okay.
So this is a possible route to post-process tars generated in biomass-based process.
Have you also seen a particulate problem?
You mean particulate?
Mm-hmm. I mean, the hand-to-hand with tar.
No, the problem with tar, it's tar. It's not one substance. Tar is a very wide family of substances, and these substances have different, distinct condensation points. So the problem around
Moves
tar,
around in your system.
yeah, where the tar condensates in your system. Sometimes it condensates together with fines and particulate matter, creating a slurry, a very, very viscous slurry. And sometimes these slurries plug your system up, and you're not able to deliver any gas anymore. So sometimes you have to heat your pipes up in order to control where the tars have to condensate. The tar had to condensate where you are able to remove the tar out. So sometimes it's like magic. You have to.
More questions? Guys from Google Classroom, do you have questions? Pedro, you're working with the...
Can you hear me?
Yes, who is talking? Sergio?
Yes, I have one question. Can you hear
Okay.
me?
Yes, go ahead.
Yes. Yes, my question is regarding your point of view to produce hydrogen from glycerin. It's maybe a big challenge because currently China buy energy.
Sergio, we can't hear you very well. Can you repeat?
Every glycerin produced in Brazil.
Can you write down maybe?
Right, I don't know.
Can you,
Oh,
Sergio,
yes, go.
can you write down your question?
What do you think about for the produce
Sergio, can you hear me?
hydrogen from glycerin? Is it possible for feasible
Tem como mandar mensagem para ele?
for the future? Yes. Sorry, it's better now? Yes. Is it possible to, you mentioned yes?
So go ahead, you can write down.
Yes, I'm hearing. Maybe not. My question is regarding to produce hydrogen from glycerin. Okay, one part.
The whole question.
You are asking the efficiency, something like that? The performance?
They mentioned something about China, because China is the main customer for today's Brazilian glycerin.
So maybe it's like a competition, or can it compete with the Chinese market, or?
Well, as far as
Se você quiser escrever, Sérgio, escreve aqui no bate-papo do Google Classroom. Como você escreveu bom dia a todos.
well, I'm not sure about Sergio's question, but
China is buying all the services in Brazil.
but not all.
So,
Okay.
Because as far as I know, Brazilian glycerin today it's close to 11% of the biodiesel derived glycerin is consumed inside Brazil. Only 11%. Another, perhaps between 40 and 60% are exported to China. And the consumption of glycerin in China, it's because a chemical compound called I think epichlorohydrin, which is a precursor of epoxy. So the reason China is buying between 40 and 60% of Brazilian glycerin is because of the production of this precursor of epoxy. But there's a surplus close to between 30 and 50% that it's not used. Sometimes it's stored, sometimes it's disposed. So sometimes glycerin is an environmental issue here in Brazil today, because we are not able to deliver all the produced glycerin for our industrial purpose. So because of that, glycerin has a small market value, and because of that, it's able to produce a low-cost hydrogen. This is why we are looking into glycerin in order to be an alternative source of synthesis gas in Brazil, because glycerin is not completely consumed or sold in today's Brazilian market.
Nice.
Is there some other important buyer or mostly China?
Mostly, perhaps only China. Perhaps only China.
So like 30% go to waste or alternative use?
Or incineration sometimes, but not purposes without value. Purpose without value. And sometimes they bury it into the soil, the glycerin. So this is an environmental issue. This is a problem.
more questions?
If no other students has any question, I would like to ask
Okay.
some. What about safety and leakage issues when you have stored hydrogen under 700 bars?
This is a very typical question, because 700 bar is very high pressure storage pressure. Compared to gasoline, for example, hydrogen has a major advantage, that is its diffusivity. hydrogen have a very high diffusivity. So in the case of leakage, the hydrogen itself is spread so quickly that you are not able to form a explosive cloud. And this is actually an advantage of hydrogen over gasoline, because when gasoline leaks or LPG, because in Europe, LPG cars are, especially in Italy, LPG cars are very, very usual. In case of LPG, when it leaks, the gas clouds remains under the car, and this is a safety issue.
Right.
So in case of hydrogen, there are two main cares related to high pressure storage. The first one, the pressure regulator is integrated with the vessel, with the tank itself. So your hydrogen lines inside the car don't have the 700 bar that you have in your pressure vessel. This is the first one. Today's class 4 hydrogen tanks, they have no metal at all, besides the pressure regulator in their composition. They are composed by a very thick and dense plastic in order to keep the vessel very sealed. Then a carbon fiber layer in order to structure the vessel, and a carbon fiber and a glass fiber layer in order to make the vessel more resistant to usual impacts. And an ultimate layer with a special foam to avoid vibration of the pressure vessel inside the car. So all the high pressure is contained in the vessel. You don't have high pressure lines inside the car.
And the hydrogen does not traverse this wall?
No,
Not at all?
No, not at all. There are some bullet tests with these vessels. They have to resist to a semi-automatic weapon target directly to the vessel, to the pressure vessel.
Just two more quick questions. About the advantages of using hydrogen as energy vector. Is there any other advantage besides the energy concentration per unit of mass?
When we compare the hydrogen-based vehicles with other electric cars, because hydrogen vehicles are also electric cars, other major advantage is the fueling time.
Okay.
Because when you fill your electric car with electricity, if you try to do that in your house, you will need probably 10 or 12 hours to reach 80% of the battery capacity. You have to get a fast charger, or a high power fast charger, in order to fulfill your battery pack. For hydrogen cars, for Nexo, for instance, the fueling time is done between 3 or 5 minutes. It's very similar to conventional vehicles. So this is other advantage. Other advantage are related to local emissions. Even when you produce hydrogen from natural gas, let's say for costs issue, locally you have no other emission than water. This is the local emission of a hydrogen car. When the hydrogen is used in a fuel cell system, because hydrogen is also a technically feasible fuel for internal combustion engines. But when you do this, you are not able to escape from the nitrogen oxides emission. So when you use hydrogen in the internal combustion. You have water, of course, but you have nitrogen oxides related to the use of hydrogen.
Understand.
But in the fuel cell-based vehicles, only water is the local emission.
Okay, just a last question. What if there were no governmental interests in renewable fuels and processes? How would hydrogen be affected with respect to its competitiveness?
For example, I told you about the applications in trains that are currently being used in Europe and in China. For these specific applications, hydrogen is feasible right now. Because of the cost of new lines construction, when we talk about usual technologies such as pure electric cars or pure electric trains, because the electric network, it's very expensive to be installed.
Right. Independent of government?
Independent of government. Yeah. Until now, the issue was to demonstrate the technical feasibility.
Right.
But once demonstrated, it's already feasible.
Okay. Thank you.
More questions?
In the same direction, about the feasibility, how much would be the cost of one unit that you showed for ethanol to hydrogen production? And what about the time life of the main components and time life of a regular fuel cell for a bus or a small car?
Okay. Well, the first question about the cost, I have no idea because I don't deal with costs. And the costs are very related to many other aspects because, for example, the nominal capacity of the plant, what kind of utilities are available or not in order to assist the reformer's operation. Então, so we have to make calculations, we have to analyze case by case what we have to provide for customers in order to give them a cost. So actually not a cost, but a price from the consumer point of view. So I don't have enough information to give you a price. But if you need, let's say, a veil for your work, we can provide you with a veil, but I'm not the people in charge inside our company. The second question is about lifetime. All the units are designed for 20 years lifetime. 20 years does not represent that before 20 years you have nothing. It's more like economic calculation and a point of reference where, for example, in the beginning of life of electrolyzer, each electrolysis cell operate under 1.8 or 1.9 volts. Each cell operates under this tension, this voltage. End of line is defined as 3 volts. So you're still able to produce hydrogen, the same amount of hydrogen, but at 3 volts, your power consumption is very high. So perhaps it's not feasible anymore to keep this machine into operation. So after 20 years, you have you are able to produce, but perhaps not feasibly anymore. Or after 30 years, you perhaps have to revamp your plant, change your stock, and this same happens with the fuel cell cars. Today, the manufacturers operate design the fuel cell stacks for 15,000 hours of operation. 15,000. It's a little bit difficult to convert hours into kilometers because it depends on the use of the car. But in the end of life, you still have power being generated, but not the original power the manufacturer warranty you in the time of the car purchase. But you are able to exchange only the fuel cell stack, not the whole car,
Yeah.
as well as for the battery cars. You are able to change only the battery pack. In hydrogen cars, you are able to change only the fuel cell stack.
Do you know what is the typical size of the auxiliary battery in these cars with the fuel direct in the fuel cell?
I think the slides concerning Nexo have this information. I think the battery is something around 3 kilowatt hour. 3 kilowatt hour. So when we compare 3 kilowatt hour with a full battery car, in full battery car we are talking at least from 45 kilowatt hour up to 100, which is the case of Tesla Model S P, which is performance. So Tesla Model S P, I think, have a 100 kilowatt hour battery pack, and I think Volkswagen ID3, which is a new electric car from Volkswagen, the smaller battery pack is 45 kilowatt hour. So range in this inside these extremes. For hybrid, this is comparable. Actually, it's comparable to a mild hybrid car, which is coming into reality also for internal combustion engines. For a mild hybrid car, which is what a fuel cell hybrid electric vehicle is, the battery packs are between 1.5 and 3.5 kilowatt hour of capacity.
More questions? I have only one. No, I have more, but I know that we don't have much time, so I'm going to ask only one. Thinking about the future, but not so far future, and thinking about
Not
the cost.
Jetsons like.
Yes, not that, not that. And thinking about the hydrogen production to use in those, or to mobility use. Do you think it is feasible to have many reformers in gas station to provide hydrogen, or to use the refinery production to transport this hydrogen to a certain distance, as you said, something about 500 kilometers, which you are going to pay more for the transport than the production of the hydrogen, something like that?
I think the problem is very related to the hydrogen for industry applications, for example. I don't think today Brazil have, I think, close to 42,000 refueling stations all over the country. 42,000. Of course, I don't think our market is 42,000 reformers for each, because the amount of the reformers depends on the fleet.
Yes.
Depends on the fleet. In areas where your hydrogen fleet is more expressive, you obviously need more reformers in order to attend this fleet. In areas where your fleet is little, only a few vehicles, I think the best strategy is to have a more centralized production and the distribution of the gaseous, high pressure gaseous product. So I think the answer, it depends on the fleet.
When we're talking about São Paulo, and we're talking about the refineries that we have around São Paulo state, maybe the production would be more interesting. The price of the hydrogen would be more interesting, producing the refinery and distributing around the area, or not?
Could be, because the hydrogen production in refineries today, the new investments are very focused in, because the older plants are, the capacity is still used for refinery purposes. The new plants, the new investments in hydrogen plants are very focused on diesel desulfurization in order to take out of the market the S500 diesel and keep only the S10 diesel with a small amount of sulfur. So the new investments looks for the hydrodesulfurization of diesel. I'm not sure these new plants are able to attend a hypothetical hydrogen fleet in next years. If the technology take this growth, perhaps the refiners could be interested in new investments to attend this. In this case, I think this is the more feasible way to attend a fleet, which are near to the refineries. However, for more isolated fleets, you have to have a on-site reformer or on-site electrolyzer in order to attend to
And the last one, is Hytron looking for the solid oxide fuel cell system and thinking about the use of ethanol as Nissan had in his car, using this type of fuel cell in our country, or is another project, or is looking for something like that?
Today, Hytron doesn't have the focus on produce solid oxide fuel cell stacks. But we are discussing some projects to build in Brazil solid oxide fuel cell systems. Since we have a solid oxide fuel cell stack manufacturer that provide us with the stacks. Because to implement a production line of a technology such solid oxide fuel cell it's very costly to implement that, and it's only feasible if you already have the demand. So if in Brazil it's eventually it develops into a interesting technology, could be a production line in Brazil. But right now we are more focused into systems than into stacks.
Okay. So you guys, more questions? No? Pedro, Sergio, are you still there? You have questions?
Do you also build the PSAs yourself?
Yes.
Okay, wow.
Yes.
You don't buy them from a third party?
No, only the molecular sieves, of course. But we have our own technology for PSAs.
So you guys, thank you, Antonio, very much once again.
Pleasure.
We hope to